Hi, my name is Catherine Fatahi, and I'll be discussing whether or not numerical cognition implies arithmetic ability. Numerical cognition is essential for animals in survival tasks. For example, recognizing where there's more food or less predators can improve one's chances of survival. However, this ability does not imply that animals can carry out more complex arithmetic operations. A study from 2019 claimed honeybees could learn addition and subtraction based on a reinforcement learning task. Here's the experimental setup. So the researchers trained the bees via a Y maze and used colors for addition and subtraction, blues for addition and yellows for subtraction. The bee would enter the first chamber and see a stimulus. This would be a number of shapes with a color. Then it would fly into the next chamber and be presented with two choices. The bee would need to go left or right. So the bee would receive a reward for a correct answer and a punishment for an incorrect answer. There are 4 non-reinforced tests. 2 are addition-based and 2 are subtraction-based. For each arithmetic operation, one test includes the correct answer and incorrect answer in the same direction as the operation. So for example, if the bee saw 2 shapes and the color blue, the bee would need to add 1 to 2. So 2 answer choices could be 3 and 4. And those are both above the number of 2, so they're in the same direction. The other tests include the incorrect answer in the opposite direction of the correct answer. Now, here are the results from that study. In figure 2a, you can see the performance of the bees during the learning phase, and you can see that it increased significantly. Then figure 2b, you can see the performance of the bees during the testing phase and their significance from chance level, which was this dotted line. And so based on this, the researchers claimed that bees were capable of learning and applying numerical cognition to arithmetic operations. So here we decided to model the experiment, and we used a feed-forward model for our initial model. There's a 4-dimensional input representing the initial stimulus. So A would be the number of shapes, B would be the operation plus or minus 1, and then the 2 answer choices, the correct answer A plus B and the incorrect answer X. So these would be inputted into our network, which would output a reward and punishment associated with the correct answer and incorrect answer. So here are the results from our feed-forward model. We did various tests. Some were simpler than others. Test 1, 2, and 3, we can see the models performed very well. Test 2 was very similar to test 1, except instead of using +1 or -1, we used +5 or -5. And then test 3 was also similar to test 1, but the 2 answer choices were in the same direction of the operation. So as you can see, the models performed very well on all these tests. Then test 4 was a shuffle test, and we did this to ensure our model did not have any bias. And as you can see, the models performed around chance level. And then test 5 and test 6 were more complicated because there was no correct answer. These tests were made to test for any biases, and what we found is that the model is not encoding addition or subtraction. It is choosing the answer closest to the correct answer more often. So there could be a different type of operation occurring within our network. So the next step is to use a long short-term memory model to count for time. And so there'd be 2 states. There'd be the first room and the second room. And each of these states would have 2 inputs. The first room would have the initial number seen and the arithmetic operation. And the second room would have the 2 answer choices. So the model would either store the added inputs from the first room, or it would compare that stored addition value to the 2 answer choices in the second room. And there are 4 actions that the agent could take. It could either stay, move, or move left, or move right. And so move and stay were associated with the first room, and move would have a small reward because you want the agent to perform the operation as fast as possible. Then moving left or moving right would be associated with the second room. And if the agent was correct, it would receive a reward. If it was incorrect, it would receive punishment. There's also a large punishment for an illegal move. For example, let's say the agent was in the first room. If it chose to move left or right, that's not possible because it has not done the operation yet. And so based on these rewards and actions, the environment would be updated. So this is our current progress. We're building a recurrent neural network with 2 layers, the add layer for performing the operation in the first stage, and a decide layer for comparing the output from the add layer with the two answer choices. So for the add layer, the input is shown for a period of time steps, but not the entire time. And this is because in the actual experiment, the bee flies into the first chamber and sees the input, but then it has to fly into the next chamber and it does not see the input anymore. But when it's in the next chamber, this would be our decide layer. It sees the input for the entire time because you can see the two choices. And so we found that our add and decide layers functioned as expected, and there's about 97.5% accuracy when the layers were trained separately and then tested together on the training data. And this was during the final time step. So here's the output from the add layer. As you can see, there are fluctuations within the first 10 time steps when the input is on. Then once the input turns off, we reach a constant value as expected. And then that continues for the rest of the time steps. And so for the output of the last 10 time steps, we inputted that into the decide layer for during testing. And this is shown during the last epoch of training. So here's the output of the decide layer. As you can see, there's some fluctuation. So we want the data output to reach either 0, 1 for moving left or right. So 0 would be left and 1 would be right. And as you can see, towards the end of the epochs, we are at 0 or 1 for most of these data points. And this is plotted from the last epoch of training. And here's the accuracy of the add layer during the last epoch of training. As you can see, just add 10 time steps when values are constant, we have 100% accuracy, so that's very good. Then here's the accuracy of the decide layer, which fluctuates a bit, but it remains consistently above 95%, which is very good. So the next step would be to create more complex tests for our model. Thank you for listening.